A and B are constants, right?
Right. You get that when you multiply it out. So, if we want where the particle's at rest, that means where velocity equals 0. Right? So, I want to take the derivative here. My derivative, if A and B are constants, my derivative would just be 2t minus A minus B. Then setting this equal to 0. I can add A and B to the other side. Let's have A plus B equals 2t. Divide both sides by 2. We get that the particle is at rest at A plus B over 2. Yeah, that would be correct.
But then if it was A and B, then it would be.
Oh, wait a minute. Yeah, so let's do product rules. So if we take the derivative of the first, that would just be 1, right? Times t minus b plus the first t minus a times the derivative of the first, which is 1. Yeah. So that's, oh, I see what you're saying. You were thinking that that was your position function still. That's your derivative. That's your velocity function. So then you would just set that equal to 0. So t plus t is 2t, right? Minus b minus a. So it's the exact same thing that we had over here. Alright, we okay with that one? Alright, then let's talk about the homework. How'd it go?
I think
2 of them?
Alright. 19.
15, 18, 19.
Oh, yeah, 19. Yeah, I got 9.
Okay, let's start with 15 then. Alright, number 15. This one I think was pretty similar to number 5 up from the other day. So first, if I take my derivative, I will bring the 5/3 down. So 5/3 times 1/5 would be 1/3, right? 5/15ths are 1/3 times x minus 4, and then subtract 1 from the exponent. So that'd be 2/3. Then plus, if I bring my exponent down, 2 times 2/3 is 4/3, times x minus 4, and subtract 1 from the exponent, I get negative 1/3, and then the derivative of negative 1 is 0. So now I want to set this derivative equal to 0. 3rd times x minus 4 2/3 plus, now I guess, let me rewrite it as I go. So this would be the same as x minus 4 to the 2/3 over 3, right? And this one would be the same as 4 over 3 times x minus 4 to the 1/3. We okay with rewriting things like that with negative exponents? So now what we talked about yesterday is I can take one of these terms to the other side and then just cross multiply. So it doesn't matter which one I take to the other side. I'll just take this one over. So we'll have negative x minus 4 to the 2/3 over 3 equals 4 over 3 times x minus 4 to the 1/3. So now when I cross multiply, I will have 3 times 4 is 12. And then here, I'll have negative 3 times x minus 4 to the 1/3 times x minus 4 to the 2/3 would be x minus 4 to the 3/3, which would just be to the first, right? So this is just x minus 4 to the first power now. Now this is a pretty straightforward equation to solve. Right? 12 equals negative 3x plus 12. Subtract the 12 over. We get x equals 0.
Whoa.
Right.
So you add the exponents and the exponents.
Yes, yeah, whenever we have a common base and I'm multiplying those things together, I would add the exponents. So, like Nicole just said, we also need places where our derivative would be undefined. So we have to go back up here and say, well, if I plug in 4, I would get 0 in the denominator, which means it's undefined. So x equals 4 is also a critical value here. So we get 2 of them. The derivative is equal to 0 at 0, and the derivative is undefined at 4. You okay with that one? Alright, and then 18.
Yep, got it.
Alright, so on 18, the derivative of tangent of 2x, what's the derivative of tangent? Secant squared. So I'll have secant squared of 2x times the derivative of the inside, so times 2.
Oh, I thought you were talking about getting rid of making that 2x2 by taking the derivative of 2x. Oh, yeah.
You do have to take the derivative of 2x. Because basically, we were just change was I just left the 2x in there and I didn't take the derivative of the middle thing after the arc.
No, we would do chain rule here. There's 2 layers, right? Tangent's the outermost layer, and then 2x is the next layer. Yeah.
Okay, so after this point, what?
Okay, they can. Well, then this.
So this time is different.
So now we would set this equal to 0, right? Yeah, we could just divide both sides by 2 to get rid of that. Just say secant squared of 2x. Now, I mean, at least for me, I think it's a lot easier to think about trig functions in terms of sine and cosine. Right? So if we think about this as 1 over cosine squared, is there any value that I could plug in here to make 1 over something equal 0? No. Right? So there are no critical points, or critical values, or critical numbers, whatever terminology we want to use.
So I have learned, like, is it anytime we have a trig function, we're gonna have no critical points?
No.
Okay. Because it just both of these had no critical points. But that would still have an x.
I mean, think about what tangent looks like. Right? Tangent looks like this. Right? A whole bunch of times. What we're finding are places where the derivative is 0, meaning we have a horizontal tangent line, or where the derivative is undefined. At no point on this graph do we have a derivative of 0. Right? There's no place where I can draw a horizontal tangent line. On some trig functions, there are though. Right? Obviously, sine and cosine do this. So there's a whole bunch of places where I would have my derivative equal to 0 on functions that look like that. Right? So what we just found is that because our graph looks like this, there are no critical points.
So anytime it's tangent, it's not.
Yeah. I mean, if it's just tangent, I mean, if we had tangent plus sine or something like that, then that would. But yeah, if we just have a tangent function, there won't be any critical points. No, because I don't think they give you credit for that on the AP test. They would want to see the work. Like they would want to see the derivative. Yeah, so no, sorry. Alright, then 19 as well. Alright, so take the derivative. So prime of x. I'll just leave that negative sign out front. Square the denominator. Bring the denominator straight up. Times the derivative of the numerator minus the derivative of the denominator times the numerator. So now I want to set this equal to 0. So I'll go ahead and simplify the numerator here. Let's see, that'll give me 3x to the 4th minus 3x squared minus yeah. So I can even clean this up a little bit more. I'll go ahead and multiply both sides by the denominator as well. That will cancel out the denominator. So I'll end up with negative 3x to the 4th minus a negative 2x to the 4th, which would be negative 1x to the 4th, right? And then plus 3x squared. So I can factor out a negative x squared here, right, and have x squared plus 3 left.
What did it be minus 3 since you took out the negative?
Yes, thank you. X squared minus 3. So set both of these equal to 0. I get x equals 0. And if I set this one equal to 0, I'll get x squared equals 3. So x equals plus or minus the square root of 3.
Okay, isn't there also an x equals 1?
Yes, so then we also have to look for where our derivative is undefined. So if I plug in 1 here in the denominator, I would get a 0. So this one has 4 critical values, right? 0, positive and negative square root of 3, and also at x equals 1.
Yeah.
So yeah, you're right, yeah. 5 critical values. You okay with those? Any other questions on finding critical values? All right, then I'm actually going to teach in class today.
No, like I watched these 5, so take it.
Take notes.
Yeah, it's honestly, I just can't stand watching you write about little figures. Like, I don't know. Because I can just imagine myself trying to write down. That would be so frustrating.
I mean, I'm still not very good at it.
Yeah, I think that's it. Are you checking this?
Nah.
You trust that we would be students?
Yes. Alright, where
Let's do this.
Probably not, since this
How
will
much is like math?
70%.
Are our tests weighted that way?
They're mastery grades.
They go, yeah, tests go into the 70%.
So what doesn't work?
Like practice grades.
Yeah, like for me, like some teachers do it differently, but for me, I put anything that's graded for accuracy into the mastery category, and anything that's for completion into the practice category. So, like for us, that includes like Khan Academies and Math XLs because those are accuracy grades. You have to get them right in order to complete them. So those go into the mastery category in here as well. I wanted to, not this way, let's do the,
Pick a color.
if you have colors, then you can use them. Come on. Alright. So, today we're going to take a look at the first derivative test. We're going to use what we've been talking about to go a little bit further. So first, we're just going to take a look at a little analysis of this graph here. So it says using a red device. If you have colors, you can use them. If not, that's fine. Right? So using a red colored pencil, circle all points corresponding to local maximum values. And don't include endpoints. Whenever we're talking about relative mins and maxes, we don't include endpoints. So where would I have local maximum? D. Any others? A. Any others? It kind of looks like it might go up there, but I don't think it does. I think it levels off and then just keeps going down. So there, I don't think we would say is a relative max. I think these are the only two. I think it's just at x equals a and x equals d. So at each maximum value, if we want to talk about what this function is doing, we can say that it changes from increasing to decreasing at every maximum value. Right? So the function itself changes from increasing to decreasing. What can I say about the derivative then? If we know derivative is the slope of this function. Right? So if I'm saying that my function is increasing, what's true about the slope? It's positive. Yeah, so I can say then that f prime, or the slope, changes from positive to negative. All right. So similarly, we can talk about local minima. I don't have a blue rating device.
I'm not following the color code either, so.
All right, so we want to circle all local minima. Where would all my local minima occur? Let's see.
Wait.
Well, so we're not including endpoints, remember. So like this and F would both be endpoints here. So I think the only place where a minima occurs is at C. So at these minimum values, what can we say about F? F changes from
Decreasing.
decreasing to increasing. Right. So then what can we say about the derivative? Changes from negative to positive. So, next, at each local extreme value, right? So we found 3 places on this graph, right? We had 2 maxes and 1 min. What is true about the derivative? The derivative is either equal to 0, right? At both of these places, the derivative would be equal to 0. So the derivative is either equal to 0 or undefined. Exactly. Here we would have a cusp. So, if the function has a relative extremum at a point, then the derivative is either 0 or undefined. Is the converse of this true? Right? So converse just means I flip the statement around. So that would be saying if the derivative is 0 or undefined, the function has a relative extreme. Does that have to be true?
Maybe.
Maybe. Yeah, no, maybe. Why not? Possibly. There's another. Why not?
If it's not continuous, then that would not be, it'd be undefined, but that would be the maximum.
Oh, yeah, that's a good point. So that's not the one I was thinking of, but yeah, that's absolutely true. So Jacob said, if the function is discontinuous, then that would be a place where the derivative is undefined, right? But we wouldn't be able to get necessarily a max or a min there. So I mean, yeah, that's a good one to write that down. There's another one though that I was thinking of that is evidenced in this graph. Well, so the whole would be the same as a discontinuity, but at the cusp we did have a local max. So what we're trying to find is a place where the derivative either equals 0 or is undefined, but there isn't a local min or a max.
How at E?
At E, right? Here, the derivative would equal 0, right? We would have a horizontal tangent there, but that is not a min or a max, right? So the converse of this statement isn't true because we could have a discontinuity, or we could have a place where the derivative is equal to 0, but there is no local min or a max, right? So we could say f prime of x could equal 0 with no change in sign. Right, so what that's saying, like at this point, I could be saying my derivative is negative, then it equals 0, but then it keeps going negative. Right? It doesn't change from negative to positive. So the point that justifies this answer is set at x equals E. Right? So what all of this leads us to is the first derivative test. So if our derivative changes signs from negative to positive at a certain point, then that point is a relative minimum. If our derivative changes from positive to negative at a certain point, then at that point we have a relative maximum. And then if our derivative does not change sign, we don't have either one, either a relative min or a max. All right, so visually, and we've already looked at this a little bit, but if we have our function, right, and we're saying the derivative changes from negative to positive, we have a local minimum value. If our derivative changes from positive to negative, changing from positive slope to a negative slope, that's a local max, plus, and we could have a place where the derivative doesn't change signs, right? Here, the derivative is positive, 0, and then positive. That would be neither a local min or a local max. All right? Questions so far? All right, so let's try one of these. Okay, so our goal is to figure out where the graph is increasing, decreasing, and then find any relative mins or maxes. The first thing we want to do is find all critical values. Okay, those are the places where a min or a max could occur. So we know how to do that. Right? Take the derivative, set it equal to 0. So 4x cubed minus 16x. Set that equal to 0. I'll go ahead and factor out a 4x. So we've got x squared minus 4. So setting both of these equal to 0, I would get x equals 0 and positive and negative 2. Are there any places where the derivative would be undefined? No. It's a polynomial. So these are all of my critical values. The next step then, to figure out all the information that we want, intervals of increasing, decreasing, and where relative mins and maxes occur. I'm going to take these three values and put them on a sign chart. So I'm just going to draw a number line. I'm going to make sure I label this as f prime, okay, because eventually we're going to do a second derivative test as well. So make sure that you label your sign chart here as f prime, and just put these three values on there. So -2, 0, and 2. Now, what I want to do is test a number on all of these intervals to see whether the derivative is positive or negative. So what I'm going to do is, for this first interval, take a value less than -2 and plug it into my derivative to see if I get a positive or negative value. Okay, so let's take -3. Okay. If I plug -3 into my derivative, now all I care about is whether it's positive or negative. I don't care about what the actual value is. So if I plug -3 in here, this would be a negative value. This would be a positive value, right? So a negative times a positive get me a negative. So I'm just going to put a negative sign on that interval on my sign chart. Right? Then if I take a number in between -2 and 0, say -1. So I'll take -1 and plug it into my derivative. So this would be a negative. This would be a negative, right? -1 squared minus 4 would still be negative. So a negative times a negative, positive. Take a number in between 0 and 2 then. Say 1. Plug it into my derivative. So if I plug 1 in, 4 times 1 is a positive. 1 squared minus 4 is a negative. So positive times a negative gets me a negative. And then my final interval, take a number greater than 2. Say 3. If I plug 3 in, this would be a positive. This would be positive. So positive times a positive is a positive. Okay? We okay with that so far? So now this sign chart tells me all of this information. First, let's do intervals of increasing and decreasing. So here, if my derivative is negative, is my original function increasing or decreasing? Increasing. I'm sorry, decreasing. So what I can say is my original function, I can say f of x is decreasing on the interval -∞ all the way up to -2. Right? I'm not going to include -2 because at -2 the derivative is 0. Right? It's not negative. Well, on this interval then, from -2 to 0, my derivative is positive. Does that tell me about my original function?
It's increasing.
It's increasing. So I can say function then is increasing on the interval -2 to 0. Then again at from 0 to 2, my derivative is negative. That means my original function is also decreasing on the interval 0 to 2. Then my final interval, my derivative is positive. That means my original function is increasing on the interval 2 to infinity. Okay. We okay with that so far? Then the second part is to find relative mins and maxes. So if I look at my chart, at x equals -2, my derivative changes from negative to positive. That means my original function changes from decreasing to increasing. So at x equals -2, I will have a local min, right? Or a relative min. So I can say local min at x equals -2. Then at 0, I change from increasing to decreasing. So at 0, I would have a local max. And then at 2, I change from decreasing to increasing. So at 2, I also have a local min. All right. The biggest thing that people get tripped up on is the vocabulary here. Right? It's very important for us to not get the positive, negative, and increasing, decreasing mixed up. A lot of times people want to say, well, the derivative is decreasing here, so the original function is positive, and they get that all mixed up. Okay? What we want to make sure we keep straight is that if the derivative is negative, the original function is decreasing. If the derivative is positive, the original function is increasing. And then for mins and maxes, if my derivative changes from negative to positive, I have a local min. If my derivative changes from positive to negative, I have a local max. Okay. We okay with that? So let's just take a look at what that function actually looks like then, okay, and what we determined. So we found local minimum values at x equals -2 and x equals +2. We found a local max at x equals 0. And we said that this function was decreasing from -infinity to -2, increasing from -2 to 0, decreasing from 0 to 2, and then increasing from 2 to infinity. Right? We found all of that information just from taking the derivative, finding critical values, and putting them on a sign chart. Right? Questions? All right, then you guys try this one. So find the derivative, set it equal to 0, find your critical values, put them on a sign chart, and determine on those intervals whether the derivative is positive or negative. What value did you plug in? So should be, right? Because that's what we found one of our critical points to be. We want to plug in a value that's on the interval. So we would plug in a value less than -2 and a value in between -2 and 0. Something that looks like this. Function is increasing from -2 to 0 and 2 to infinity, decreasing from -infinity to -2, 0 to 2, which means we have a local min at both -2 and +2 and then a local max at 0. So our function looks like this. Right? Local minimum values at -2 and 2, and local max at 0. Okay. So we actually found a lot of the same information between those two examples, right? Even though our graphs look very, very different. And this kind of illustrates how important it is to make sure we include places where the derivative is undefined. Okay, that's also a common mistake to forget to include those points, but those were important. Right? We had local mins at both of those values. Okay. Questions? All right, we probably have time for one more. Okay. I think we do.
No, we do 8 in that. Or 8 what? I thought that was 8. We do not 8 columns.
I think we do.
Sign. Oh, you're recording.
Yes.
Were you recording her? Sure, I said you.
No, I am recording
Thank
now.
God, that's embarrassing. Oh, I wish. Totally. On Sunday when I do episode, I'm going to do the same one to every single one of these. I'm going to dumb stuff I say this class. I just don't remember it.
Oh yeah, you guys got to the alpha two.
Does it, I don't know, what is the cosine of like 5 pi over 3 or whatever? How much is that? How do you figure it? So long as it's going to, how do you just know that? I said it. It's 11. They must have told me all the time. How am I supposed to do?
So how did you put numbers?
Well, you can just think about the unit circle.
That's too hard.
Right? So if I'm plugging in a value in between, well, first, here and here, right, is cosine, so my derivative is 1/2 minus cosine. Is cosine going to be greater than or less than 1/2 here? Cosine's the x value, right? So over here, on this piece, the x value is greater than 1/2. So I would have 1/2 minus something greater than 1/2. That'd be negative. Then here, I'll have something less than 1/2 on this entire piece for cosine. So I'll have 1/2 minus something less than 1/2. Positive. And then same reasoning here. So over here, I'll have something greater than 1/2. We're not
All of these?
gonna class tomorrow, so
Why not? Oh, yay. I really don't
this
want
is
to
like
go.
2 days worth of work.
Alright, I'm doing it. I just like, oh, we're not here.
Yeah.
Or next. No. Wait.
Oh, wait. How do you use your read, please?
So we're not gonna have class tomorrow because we're going to the health fair.
Wait, tomorrow's Friday, right?
Tomorrow's Friday. So tomorrow, don't even come here. Just go straight to the pack tomorrow. Okay, I'll take attendance down there. Yeah, have this done for Monday. I will though want to collect your AP practice tomorrow, so get that to me at some point tomorrow.
Oh, I wanted to ask you a question about